This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello, this is Nishant Suneja from Software Engineering Radio. Today I'm speaking with Max Neunhoffer. Max Neunhoffer is a mathematician turned database developer. In his academic career, he has worked for 16 years on the development and implementation of new algorithms in computer algebra. Recently, he has returned from University of St. Andrews, where he was a lecturer, to Germany. He has shifted his focus now to NoSQL databases and now helps to develop ArangoDB. He has spoken at international conferences including O'Reilly Software Architecture London, J on the Beach, MezosCon in Seattle, among many others. Welcome to Software Engineering Radio, Max.
Hello.
So today we will be talking about all the significant aspects of multimodal databases in general and ArangoDB in specific. Great. So Max, let's start with something basic. And I just wanted to, I know that NoSQL databases have a lot of definitions. I just wanted to get your perspective on how would you define a NoSQL database?
Yeah, first of all, one ingredient which seems to be necessary is that it does not do SQL. But essentially, the term cannot really be defined because it covers by now such a wide variety of completely different data stores that basically the only thing you can say, it is not just relational database. And if you look what happens in this space, then you cannot even say that you relax asset semantics or whatever, because many NoSQL databases, although they don't do relational and they don't do SQL, add transactions and add joins and all the rest of it. So therefore, the term doesn't have a proper definition.
Right. So NoSQL databases do have a hazy definition because it encompasses a lot. So what are the different types of NoSQL databases?
Okay, so first, one dimension you can distinguish is the different data models. They are not only relational databases, but you have document databases, you have graph databases, you have just key value stores, you have columnar databases, you have even time series databases, and I probably forget a lot of these things. So the data model aspect is one defining factor. And here there's even something like ArangoDB, which is a multimodal database supporting multiple data models. But the other big aspect is the kind of guarantees that data store is giving to you. And again, this is in a sense independent from the data model. And a lot of NoSQL databases have chosen to offer more availability promises as opposed to consistency promises. And that's just not a binary choice, but it's a whole spectrum of possibilities. And that's a second dimension of differences. So I would say there's data model differences and there is consistency guarantees and other guarantees differences. And that is essentially what defines what type of data store you are looking at.
Makes sense. Like the data modeling and like you said, consistency guarantees are the two defining criterias for any NoSQL database. So like you talked about different types, I just wanted to get into a few of them and understand what they are. Let's start with document store. We did a show on MongoDB, which I have put in the show notes. I just wanted to understand how would you define a document store?
So first of all, with document, one usually means a JSON documents. That's a highly recursive data structure, quite simple in its syntax, but quite powerful because you can do lots of different data structures with it. Now, a document store would be a database which stores document. And the analogy to the traditional database world is probably that a document corresponds to a row in a table. And what is a table corresponds to a collection of documents in a document store. So the thing is, every row in a table has to have the same format and the same types of entries in the columns. But in a document store, every single document in the same collection can have a different structure. And that is what is one of the big strengths of a document database.
I see. So that also means that you can, I think one other thing which document stores are good at is creating bunch of secondary indexes on the different attributes in the JSON payload which we are storing in the collection. Is that correct? Is that a correct statement?
That's right, exactly. Although the documents can have varying structure in a collection, you can still ask for secondary indexes, you can have sorted indexes, you can have hash indexes, you can even have things like geo indexes or full text indexes. And what you usually do, you specify this should be on this and that attribute of all the documents in this collection. And obviously the document store and the index has to be prepared that this attribute is sometimes there and sometimes not, because the documents can have different structure in the same collection.
Great. So moving over to the next type of NoSQL database which I wanted to talk about was the graph database. So we did a show on Neo4j, which is the episode 194. And I have also listed it in the show notes. So again, how would you define a graph database?
Right. So first of all, we have to clear what graphs are. Graphs in this context are things consisting of vertices and edges. So the vertices are somehow nodes in the graph, and the edges always go from one vertex to another. So it's essentially a kind of relation between the vertices. Now, a graph database not only stores such graphs, but also makes it possible to do graph queries. So let's understand what the typical graph query is. Usually when you have a graph, and let's make an example, for example, a social network where one person follows another, say on Twitter or whatever, that would be a typical graph, because the people would be the vertices and there would be an edge from person A to B if A follows B. Now, the typical questions for such graphs are: start at one point, maybe a person, and explore the vicinity in the graph. See who this person is following and maybe who they are following, and go a priori non-defined number of steps potentially. And so that is what a graph query does. It starts in a point in the graph and follows edges to see what other vertices can be reached. And so what makes a graph database is really that it can do this kind of graph traversals.
Right. So can you tell us that why is such kind of a traversal difficult to do in a relational database?
Yes. So the usual idea you do when you store a graph in a relational database, you would have one table for the vertices and another table for the edges. And every edge would simply refer to two vertices by a foreign key, and that's it. That's okay for storing the graph. But the moment you want to follow a path in the graph following the edges of a depth, say, between 5 and 10, you are in deep trouble with a relational database, because you now have to do a query which does 5 to 10 stacked joins. And that is something which can, first of all, be very difficult. It's very difficult to express in SQL, and when you run it, it is quite inefficient. And a graph database has typically a good language to express such questions, and then a good engine to quickly retrieve the results.
Right. So we will come back to the graph databases and discuss in more details how a native graph database like ArangoDB makes such queries faster in more details. But for now, I wanted to quickly discuss the next type of NoSQL database. We have done which is a key value store. We have done shows on Cassandra and MultimodDB in the past. I wanted to know, how would you define a key value store?
Well, key value store is in a sense the most simple of all data models. The only possibility it does, it maps a certain key space to values. And values are usually opaque to the database. They can be JSON values, but they can also be just binary data. And the only query possibility this database offers is to look up keys and find the values. Sometimes the key space is sorted, and you can also do range queries on keys. But the idea is always the same. You look up keys and find the corresponding values. And that's all you can do. But since this is quite limiting with respect to the querying, it allows for a very efficient implementation and for a very, very good scalability.
I see. So the scaling and partitioning becomes very easy because there is just one key on which you can, or rather one index on which you can look up. It's not trivial to add a secondary index, or rather might not even make sense to add a secondary index to a key value store, which actually also makes, from what I understand, scaling easier.
Exactly. For scaling, you can simply shard by the value of the key. You can take a hash value for the key, or you can do range sharding. And since the database doesn't know what the value data is all about, it doesn't understand it, there's no possibility to add any kind of secondary indexes in general. And on the other hand, scaling is easy. You can just compute where would the value for that key be, and then ask the corresponding shard.
Right. So one other type of NoSQL database which I wanted to talk about, which I wanted to know, will you classify it as a NoSQL database, is a search engine. Is search engine a NoSQL database, or is that not different than a document store with full text indexing that implements relevant search on the text indices? What do you think about that?
Okay, first of all, if something is just a search engine, it's usually not a database at all. Okay. Because things like consistency guarantees and transactional behavior and taking efficient transactional write loads and so on are all things which I would attribute to a database, but a search engine doesn't really have to have that. So you can always have a search engine which takes an enormous amount of time to ingest data, doesn't offer any kind of transactional functionality, but once you have indexed it, it can retrieve and find stuff in a very flexible way. So that's the sweet spot of a search engine. Now, of course, nowadays, the borders between the world of databases and the world of search engine has become somewhat fuzzy. That is because more and more databases add more and more advanced search, like, for example, ArangoDB with Arango Search coming up. But then also traditional search engines allow for online modification and even for transactions sometimes. So they move towards the space of databases. But I think it's still solid advice to not trust a search engine as a primary source and primary place to keep your data.
I see. Yeah, that's an interesting point, that search engine are more suited for read-only workload after the data has been ingested via a background ETL job, rather than databases which support stronger write semantics like ACID guarantees, which a search engine won't have. So we have covered now 3 different types of NoSQL databases. So apart from that, there are 2 other database types which I quickly wanted to discuss was time series database and wide column databases. So can you tell us like a brief description of what they are?
Yeah, first, time series database is specialized to ingest data from a time series, that is a stream of incoming data. And as always, when we talk about a data model, we have to talk about the querying possibilities as well. And for example, what time series databases are very good is, first of all, ingest a high volume of time series data. And secondly, offer query possibilities like having a sliding window on the data and do some kind of accumulation just over that window, but then of course slide it over time. So a typical application would be you ingest the quotes for some stock exchange, and you would like to be able to have some kind of aggregation over the last 24 hours and keep that up to date all the time. So that's a different data model which is required to offer that kind of possibilities. And Columnar Store is essentially a possibility to store tables, but whereas in most relational databases you are mostly interested to retrieve full rows, a columnar store is optimized to very, very quickly run through a column of the table. So essentially, when a relational database stores data, it does so row by row, and a columnar store would do it column by column, such that you have a high amount of data locality when you go down a column. And so they are just optimized for different queries.
Right. That's an interesting point which you brought up. It's with columnar databases, there is always this confusion regarding wide column databases like Cassandra or HBase, and complete truly columnar databases where the database also is laid out in the column format rather than row format. So when would I use one over the other?
Typical for analytics, where you have a huge amount of data and you are interested in aggregations over a single column, then you would use a proper columnar store. And these wide columnar stores are useful for other purposes as well. So you can have multiple views there and also use it more like a relational database. You don't get the ACID semantics usually, and you still get some of the optimization possibilities for a proper columnar store. But you have more flexible possibilities to also query multiple columns at the same time.
I see. Great. So now that we have firmly established NoSQL database, gone over different types of it, my next question to you is about polyglot modeling and persistence. How would you define polyglot persistence?
That's an interesting one, because I would define polyglot persistence as using the right data model for the right part of your project. This is not how it was traditionally defined. Traditionally, it was defined as using the right data store for the right part of your system. Now, that of course assumes essentially that if every data store just has a single data model, then the two definitions are the same. On the other hand, with the advent of multimodal databases which support multiple data models, my definition with the usage of the right data model for the right purpose makes more sense, in my opinion, because it essentially says that you should look at your data project, you should look at different parts, and you freely choose the right data model for the purpose at work. Let me just give you an example. If you would do an e-commerce system, you would probably use a key value store for the shopping basket in your system. For your product catalog, you might use a document store. And for your recommendation engine, you would use a graph database. And that all makes sense. And now the question is, how many data stores do you need to do all that? And the traditional polyglot approach means that you have separate data stores for each of these parts. And now with multimodal databases, you have more possibilities.
I see. That was a pretty good description of polyglot persistence, and I think you also covered the e-commerce example which I wanted to go over. So you described different use cases in an e-commerce scenario where all these three different types of databases, document, key value, and graph will be used. But if I have to generalize the use cases of these three particular types of NoSQL databases, which is to say that when would I choose one over the other, what are the criterias which someone who is doing a data modeling should look for?
I get this question quite often, and there is an actually quite simple universal answer to that. Don't look at the data first, but look at the questions you have about the data and the queries first. You, for example, notice that, like in the shopping basket scenario, the only question is, give me that shopping basket of customer XYZ. And you notice that the only type of query is this kind of key value lookup. Then you know you need a key value store. And if you further find out that you need high availability and high scalability, then you know you have found the right data model. On the other hand, if you notice that you have a very complicated questions in a recommendation engine, you know you want to look at things like look at all the items one customer bought, then look at maybe another customer who bought the same item, and then maybe look further around what these people bought and what preferences they might have, and do a deep analysis of all this data, and in the end come up with a recommendation for user B by looking at user A. This sounds a lot more like exploring linked data and doing complicated queries in a graph. So therefore, the graph model is probably more suitable. And if you then decide how to store the data, and then probably things fall into place and you know what to do. So therefore, my advice is always look at the queries you need and the questions you want to answer about your data. And once you have that, you are 50% of the way to find the right data model.
Great. So one other thing which I wanted to ask, because we talked about using these three different types of NoSQL databases and scenarios under which, or use cases for which you will use them, when would I want to use a relational database over all of these three database NoSQL databases which we just discussed?
Yeah. So if all your data fits on one machine, you don't need a very highly resilient setup, and you need ACID semantics. Then a relational database is still pretty good. So it's not bad what has been researched in 30 years of database research. It is more if you have further requirements which a relational database cannot fulfill, like very high scalability, different data models for different types of queries, and so on, where you are somehow forced to leave behind the relational world. So if you have rather homogeneous data, like say a customer database where you know what kind of data you want to store about that customers, and you might have something which you can put in an extra table like the addresses, then the relational model is perfectly fine. But if you need higher scalability, if you need graph traversals, or if you need very high throughput with key value lookups, then it's probably not so good an idea.
I see. So on what you said, how would a sharded relational database compare with, let's say, any other NoSQL database? Because one thing which you brought out is that the scale, it's difficult to scale a relational database. So how, if we shard it across multiple machines, will that not work as good as a NoSQL database?
No, I don't think so. And the reason is the following. The relational model uses data normalization. That's in principle a good idea, but essentially it means that you have to massage your data until it fits into tables. That is all fine, and that has good properties, and there's a lot of mathematical theorems about that. That's all fine. Except that the moment you have somehow taken apart your data and massaged it into tables, you then have to decide how to shard these tables. And what you then will need is join operations. So the moment you have done the data normalizations and you have put everything into tables, to do queries, you will have to do joins. And if you have a distributed data set, then joins can be a challenge. Namely, because if everything is on one computer, you can very quickly find the parts you have to join together. But in a distributed system, you might run into the problem that two things you want to join just reside on different machines. And then you have a forced latency to get them together via the communications. And so therefore, the way people have to massage their data into tables to use the relational model successfully is in direct contradiction to high efficiency when you shard. Whereas in a NoSQL database, you have other possibilities. You have the possibility to embed stuff. You have the possibility to have more flexible data models to make the sharding such that the performance of the queries is better.
I see. So it's basically the normalization of data in a relational database, which comes in the way of scaling it successfully when compared to a NoSQL database.
Yes, that's the one thing. And the other thing is, once you do SQL, you have to be fully ACID compliant because the standard prescribes that. And that's another thing which is in some kind of resistance against scalability.
Great. So we talked about what is polyglot persistence. Can you tell me what are the benefits and overhead of a polyglot persistence scenario?
Right. The benefits is you can use the right data model in all places. Therefore, your queries tend to be very efficient, and you have to do probably less data conversion to massage the data into the format which is actually stored in the database. So that's two advantages, I would say. High performance, easy data modeling because you have a lot of flexibility. Now, if you, for example, take a document store, it will usually be schema-less. So one disadvantage with the schema-less is it gives you great flexibility, but if you are not careful, then you have very dirty data, which is not very uniform and difficult to work with. So I always say, yes, usually it's schema-less, but in the end there has to be a schema, otherwise you cannot really properly work with the data. Now, when it then comes to implementation, if you need to need multiple data stores for your different data models, then you have a consistency problem, because you might have to store the same data in two different data stores, and this means you cannot have a transaction spanning both of them. So therefore you have to work hard on the client side to keep the two copies of the data in sync and to keep them consistent. So you have more consistency problem. Furthermore, you have more technological overhead. If you use 3 data stores in a project, you have to pay 3 times license fees, you have to pay 3 times for support, you have to teach your people 3 times to use a product, and you have to work with maybe 3 different providers and have 3 different manuals to work with. And that has additional operational costs. And so therefore, I like the definition of polyglot persistence of using the right data model, because this now opens the door to use a multimodal database to have both benefits. You have the flexibility of data modeling and the high performance for your queries, and yet you don't need 3 different data stores, but maybe get away with 1 or maybe 2. And that is why multimodal is, in my opinion, so attractive. It can lower costs, it can speed up the development, and therefore it can altogether simplify things.
Great. So yeah, that's a good segue into multimodal databases, because one of the overheads of polyglot persistence which you described was storing the data redundantly and then ensuring that they are in sync, which basically requires setting up multiple data pipelines between different data stores. Coming back to the example of e-commerce website, which we discussed while discussing about different types of NoSQL databases, how would I do the same thing in a multimodal database, and at the same time giving the guarantee that the data is not stored in a redundant fashion?
Yeah, this is a very, very good question. If you have the wrong type of multimodal database, you might actually have that problem because there is something I call native multimodal databases. In a native multimodal database, you have multiple data models supported in both the storage and in the querying, but it's not actually held in redundant copies. Like if you take, for example, ArangoDB, essentially we store all the data in documents, so essentially we use the document model. However, to be a successful graph database at the same time, what we do is, yes, our vertices are documents and the edges of the graphs are documents as well, but we have very, very efficient special indexes to find the edges which are adjacent to a vertex. Because that is the fundamental operation you need in a graph database. You need to very, very quickly tell what are the neighbors, what are the adjacent edges, and what are the neighbors of a vertex. But if you use the document model and essentially put the right indexes and query implementations in place, then you can do this natively. Yeah? And at the same time, you can combine key value. And so therefore, these three data models which we are using, document database, graph database, and key value, fit together in a union. They fit together such that the data does not have to be duplicated, that it's just to have different query engines which query the data according to the data model and can then also be combined in the same query language.
I see. So we will discuss more about how ArangoDB makes it possible. But before we go over there, I quickly wanted to discuss one thing. In episode 218, we did a show on CQRS, which is the Command Query Responsibility Segregation, which basically means you design your data model in such a way that your write and your reads are going to two different data stores, so that write can scale better than and they are not bottlenecked by the reads. So how would you, if it's even possible, compare multimodal database with the CQRS style of data modeling?
Yeah, so I would say a native multimodal database tries to prevent the complexity you get by putting the writes in one place and getting the reads from another. So by combining this and leaving everything in the same engine, yes, you have to have some compromises. Obviously, if you have a very, very heavy write load, it might slow down your reads. That's right. But on the other hand, you have all the you lose the complexity of having to move the data from the place where you wrote it to the place where you read it from. Yeah. So I would imagine that both technologies have good use cases. But I think the difference is that you avoid this complexity at the cost of potentially lower performance if you do both writes and reads.
I see. Yeah, I think in that manner, CQRS has same kind of bottlenecks like a polyglot persistence model, in which we have to work pretty hard to keep the writes synced with the read, so that the read queries don't serve stale data. So now that we have brought ArangoDB, we have discussed about multimodal databases and briefly about ArangoDB. I just wanted to understand that ArangoDB, from the website, I saw that ArangoDB supports three different models, which are document, key value, and graph. Why does ArangoDB only support these three models of NoSQL database and no other, which we discussed earlier in the show?
Yeah, that's a very good question. We figured relatively early in the process that these three data models fit together rather well. If you say you take a document store and treat it as a key value store, that is, you don't use secondary indexes on your values, then you are nearly there. So those two go together pretty well. But a graph database, as I explained earlier, also fits quite well, because with the right index and the right graph traversal engine, you can use the document model and still have an efficient graph database. If you look at other data models like time series or columnar store, they don't really work well with the first three. So therefore, if we wanted to support that, which would not be impossible, but we would then run into these problems that the data models don't fit together well, and you essentially have to decide in which kind of format you store. So that is a decision we didn't have to do for these three data models, but for columnar or for time series, we would have to store in a different way. And then we lose these advantages to be a native multimodal database, and would be essentially back to polyglot persistence with multiple data stores, okay, in one package, but still.
I see. That's a good point, that for a multimodal database, the different models have to be somewhat related to each other, such that you don't have to, again, come back to storing data in a redundant fashion and lose all the good things which a multimodal database brings.
Yeah.
So you just mentioned about ArangoDB being a native multimodal database, and there are certain databases out there which have a layered multimodal approach. So can you tell me what is the difference between a native database and a layered native multimodal database and a layered multimodal database?
Yeah, so what layered multimodal databases do is they essentially implement one data model as the lowest layer, typically a sorted key value store. And then they put on top of that a separate layer, which, for example, might implement documents or might implement graphs or whatever. Now, from an architectural standpoint, that's a good idea because it separates things nicely, and it separates these layers, and it looks quite neat. If you, however, then consider high performance, then you find out that suddenly the upper layers have to know about the intricacies of the lower layer, and the lower layer has to be prepared to support the right queries for the higher layer. And you either really very much interlink the two, then you are essentially back at a native multimodal database which has all in one package, or you sacrifice performance. And that is why we have chosen to go the native multimodal way, to really integrate everything into one engine with a common query language, which allows to mix and match built data models even in one query.
Right. So can you briefly explain, just to establish for the listener a clear difference between native and layered multimodal, what exactly makes ArangoDB a native multimodal? Is it the way the data is stored in the storage engine in a non-redundant fashion that makes ArangoDB a native multimodal?
Yeah, what it makes it native is that the three data models we support are all implemented in the same core with the same query engine and optimizer, and don't need any kind of redundant store or separation of concerns. In a layered approach, you would have one fundamental data model which underlies everything, which is the core implementation, and then you would have on top other features, but most of the time performance cannot be as good as with an integrated solution.
I see. Yeah, because while I was researching on this topic, I came across documentation which mentioned that each document of an ArangoDB collection has these native _to and _from _id and _key attributes, which are used to establish relationships between one model, between three different models which we have. From that, I kind of got an idea that that's how ArangoDB is basically preventing storing the data in a redundant fashion.
Yeah, that's right. So once you have edge documents, you have the from and the to as built-in attributes, which are also enforced. And in a sense, this is a kind of schema. And since we know that this is an edge collection, we know that they exist, and we can be pretty quick with the indexing and with the finding of neighbors. And that is essentially what makes the graph engine tick on top of the not on top, but integrated with the document storage layer.
Great. So now that we have discussed about some basics of ArangoDB, I wanted to deep dive into an ArangoDB cluster, because that's one of the important use case which brings out the power of any multimodal database. So can you briefly or maybe elaborately describe different components of a ArangoDB cluster?
Yeah, so first of all, as an overview, an ArangoDB cluster is fully fault tolerant and does not have a single point of failure. So how do we achieve that? Essentially, in the center of the cluster is an arrangement of usually 3 or 5 special ArangoD instances, which we call the agency, and which is a highly redundant and fault-tolerant key-value store using the Raft consensus protocol. So that is where we keep the cluster configuration, and that is where the failover algorithms and redundancy algorithms are actually implemented. So that is not the part which does the high-performance data manipulation. So that is essentially, you should imagine that central part, the agency, as a slow key-value store just for the cluster configuration. But it's highly resilient.
So that, I think the equivalent, open source equivalent of that will be Zookeeper, for example.
That is right, except that our ArangoDB agency is also open source.
Okay, that's a good point that you.
But in other programs, in other setups, you have etcd as such a central component, for example, for Kubernetes. And for example, Kafka uses Zookeeper in exactly the same way as we use our Raft ensemble, which is created with ArangoDB itself. Apart from that, we have 2 different types of instances, the so-called database servers and the coordinators. And they play very different roles. The database servers, they hold the bulk of the data, perform the replication, and also for the queries, perform the bulk of the work for the query engine. The coordinators, they take the client requests and are aware of the structure of the cluster by talking to the agency, and do the query optimization and distribution in the cluster, and then work with the database servers to fulfill the actual queries. So every client request comes into one of the coordinators, and you can choose an arbitrary one because that is fault tolerance on that layer. And so that gives you a scalable layer doing query optimization and talking to client requests. And independently from this, you can scale the database server layer by adding more capacity for queries and more capacity for data. And so everything you send to the database goes to a coordinator. It assembles the right data pipeline within the cluster by talking to some database servers. And in the end, the result will again be sent out from the coordinator to your client. That's the basic structure. We have further components. Like, for example, for monitoring, we have Sidekick containers to export Prometheus metrics, and we have a separate system to do data center to data center replication. That is all running in separate pods in Kubernetes, or it's running in separate processes if you run without Kubernetes. And so that essentially altogether makes up the complete cluster system. But the basic thing is the coordinators and the database servers.
I see. So I think that's a good thing which you brought up, that these 2 components, coordinators and the database server, kind of separates, kind of makes scaling the storage and the compute separately easier, because there's a clean separation of coordinator and the database server. So if there is no more load on the system, read load, for example, you could perhaps just add more coordinator nodes, because that's where that's the first layer or first component where the query hits. And if there is more storage load, then you can add the database servers.
Exactly.
Great. So I wanted to quickly talk a little bit about database servers. So there are two different kinds of database server, if I'm not wrong: the primary database server and the secondary database server. Primary are the ones which support synchronous replication of writes. So I wanted to understand that when for a primary database server, when the replication happens, the synchronous replication happens from a leader to a follower. What happens when the follower is not available? Since it's synchronous replication, how do we acknowledge the write, or do we fail the write? What happens?
Okay, that's a very good question. Please remind me to come back to the secondaries later, because in the latest version of ArangoDB we do no longer have them. But you have asked about synchronous replication, and this is handled by the primary database servers, and it's handled in the following way. If you configure the replication factor for a collection to be, say, 3, then this means that there is the leader, that's the primary, who has the primary copy of the data, and 2 copies, that is 2 followers. So every write first goes to the leader, that's the primary, which has the primary copy of the data, and is synchronously replicated before we tell the client that the write is actually acknowledged. So it is replicated to every replica before we go back to the client and tell about success. Now, if a client, if a database server, which is a follower, becomes unavailable, we can temporarily drop that follower and say this is no longer in sync. So that happens after a timeout of a few seconds. So if the server is a few seconds away, then this database will decide, for now, I will no longer replicate to that replica and still confirm that I have the data. Now, obviously, behind the scenes, when the server comes back, it's automatically brought back in sync, such that future requests can then again be done in a synchronous fashion. And likewise, if the leader has a failover, if the leader fails, then there is something in the agency which essentially fails over this leadership to one of the followers which is currently in sync. So that means that in either case, you have just after a few seconds that you have availability again.
I see. So if a follower fails, then for a replication factor of 3, so we make the write to 2 of the replicas and go forward, acknowledge the client. Is that correct?
Yes, that's right.
And then in the background, we have some kind of an anti-entropy tool which brings the replica which has fallen behind up to date when that node, for example, comes up. That's
right. But in most cases, this is not necessary because the replication can happen synchronously. And if there's no delay, then we wait until all replicas have replicated the data, and only then tell the client.
Okay. So you mentioned about secondary database servers, and from what I understand, they are the ones which get the asynchronous replication stream from the primary database server and are used as backups. So how far behind is the stream? How far behind are the secondary database server from the primary database server, because this is asynchronous replication?
Yeah, so first of all, for the cluster version of ArangoDB with the currently published versions, these secondaries do no longer exist.
Okay.
Since it's asynchronous, we could never really make guarantees to not lose data at a failover, and so therefore we have for the cluster abolished that. Now for a single server, you can still use asynchronous replication to replicate essentially every write to a second instance, and that is asynchronous and is usually behind, if you have a fast network, on the area of milliseconds. So it's still pretty good, but obviously we cannot make any guarantees. If the primary fails, then your replica just does not have all the data.
Okay.
We have a special deployment mode, which we call active failover, where we exploit this kind of technology. And there we still have the primaries and the secondaries, or we call them leader and follower again here. And there you have an automatic failover, and you can put a load balancer in front of that. But still, you cannot guarantee there's no data loss in case the leader fails. On top of all that, for the cluster, which at this stage only does synchronous replication as discussed, we have a further data center to data center replication which sits on top of the cluster. And that is also asynchronous in nature. And here the idea is that people use the cluster and synchronous replication within a data center to have a resilient data store there. But for completely disaster recovery scenarios, like really a complete data center failing or going up in flames, they use data center to data center replication. Yes, it is asynchronous, but since it's highly scalable, it's also usually on the order of magnitudes of milliseconds behind. And so therefore, most of the data is still there, which is mostly good enough for a disaster recovery scenario.
I see. And I believe this feature of inter-data center asynchronous replication is currently available only in the Enterprise Edition.
That is true. That is one of our enterprise features. We carefully try to make it so that the community version is fully functional and can actually be used in production without much restrictions. And we figured that this kind of disaster recovery scenario is mostly used by big enterprises who would buy a license anyway.
Makes sense. So one last aspect of ArangoDB cluster which I wanted to discuss was as to where it stands when it, I think we briefly talked about it, but where it stands as when it comes to CAP theorem. From what I understand, it's consistency and network partition, the CP more than AP side of things. Is that correct?
That is absolutely correct. That's an intentional decision we made to make it distributed, but of the CP kind. You never can prevent network partitions, and in case of a partition, we value consistency over availability.
And from documentation, it says that the cluster, ArangoDB cluster, has a master model. Does that mean that the same shard of data is stored on two different masters, is served by two different master servers, and if there is a conflict, then we have some sort of a conflict resolution?
Not really. So this master or master-slave is, in my opinion, a big buzzword. And what we have chosen is a middle ground between the two extremes. Yes, one can truly say that we are master to master because you can essentially write or read from any coordinator and you always get the same consistent result. So in that sense, from a client perspective, it is master because you can simply write to everybody and you can use a load balancer in front and it is all fine and highly resilient. Behind the scenes, we choose for efficiency and consistency reasons a master-slave model, where we say for every single shard of our collection, at all times, one database server is the leader for that shard and the others are followers. Now, you as a customer, you don't notice that because you talk to any of the coordinators and it will at all times redirect your request to the right leader that will replicate it to the followers, and without you noticing, you get the response that everything is fine. If that leader fails, behind the scenes again, we replace it by a completely in-sync replica, and that very same coordinator you are talking to will instantly switch over and from now on to talk to the other leader. And so without noticing to the outside world, we have failed over and have switched leader and follower. And therefore, the whole solution is essentially isomorphic to a master-master thing, But we don't have the problem of conflicts because they can never arise. Every single write goes through the current leader, and we can serialize writes to the collection in this way, and therefore we can never have a kind of contradiction or conflict arise.
Right. So, yeah, that's what I also gathered, that the terminology of master was used because any node could technically take write for any shard, and not because that there are two different leaders for the same shard, which would I guess make things go on the AP side rather than CP side of things.
Yes, and there's a big danger that this kind of internal conflict resolution will in the end surface to the customer.
Right.
And this cannot happen with our solution.
So moving on, I wanted to discuss about the storage engines which are used in ArangoDB. But before that, can you define what is a storage engine?
Yeah, that's in general a very good question. For us, it's quite clear. We call the storage engine the machinery which underlies a single database server to persist the data to its disk. So a storage engine is very much a node local thing for us, and it works best if it's actually attached to local storage like a local SSD. And currently, I think I can move on immediately. Currently, we have two storage engines, and you can configure your Arango instance to use either one of them. One is the one we had first, which is called files. It uses memory map files, but it does all indexing in memory. So therefore, it is optimized for cases where all your data fit into RAM, including the indexes, and it is very high performance then. The second storage engine we offer is based on RocksDB, so we simply use the RocksDB library from Facebook on each database server to persist the data. And as you might know, RocksDB is itself a sorted key-value store. So therefore, we realize all the indexes, including the edge index and all the data storage within RocksDB based on its key-value model. And that is optimized for the case that not all your data fits into RAM, and is very good in keeping a hot set in memory and still allowing you to use the full capacity of your locally attached SSD or disk.
I see. Right. So I think like the indexes which are in ArangoDB, the behavior and what kind of queries I can make against them is tightly coupled with what kind of storage engine which I'm using in the background. Is that a correct statement?
That is correct, although we try to hide as much of that as possible. So we keep the same names. So for example, you can still create a hash index even on RocksDB, but in the end, behind the scenes, it's a key lookup in RocksDB where it ends. But they should behave identical, but the details of the performance are a bit different depending on the storage engine.
Right. So like from what I understand, if like you mentioned in RocksDB, the keys are so stored as sorted key value pairs, which makes doing range queries much easier or much faster if you have a RocksDB storage engine as compared to an file storage engine. Is that correct?
That's not quite correct, because as a replacement for files, yes, we have the persistence just in memory map files and essentially an append-only store. But if you need range queries, we have a skip list index in memory. So there you can probably even faster traverse your range query and look up range sorted indexes. But of course, the index and the sorted thing has to fit into memory.
I see. So now that we are talking about indexes, one index which I was particularly interested in discussing is the edge index, which is basically the core data structure which is used for serving any kind of graph query. Can you describe what does an edge index look like in ArangoDB?
Yes. So the key role the edge index plays is that we have an edge collection, that is a collection of documents which contains all these edges. And since their from attribute describes from which vertex the edge is coming from, we need to very, very quickly find all the edges which come from a given vertex. So that essentially means we need a very fast index on the from attribute for the edge collection. And the same with the to collection if you want to go edges in a backward direction. Having said that, it's not only necessary that you find all the edges quickly, but also we must be able to update that index quickly. For example, if you remove an edge. And imagine you have something like a supernode where you have a vertex which has 1 million outgoing edges. You still must be able to remove an edge pretty quickly, even if it is incident with that supernode. And that makes the data structure for the edge index interesting, because it can essentially insert and remove a single edge in constant time, but it can list you all the edges incident with a vertex in time which is proportional to the number of edges in the result. And that is the crucial ingredient. Now, just one more word for RocksDB. In RocksDB, we use essentially a sorted index on the from attribute here. But to make this very, very high performant, we have in front of RocksDB a special cache sitting which can answer this question about the adjacent vertices and edges very, very quickly once it has been asked before. And that is particularly interesting because RocksDB is a transactional key value store. So the challenge there was to find a data structure in memory which can cache the result of such a range query, say, and still give you the transactional semantics of RocksDB. So in particular, it needs to be a cache hit if the transaction with which you're reading this still would produce the right result. And it has to invalidate the cache if you start a new transaction where this doesn't count anymore.
Yeah, that's definitely interesting. Since we're talking about the graph indexes and next I want to talk about transaction. But before going over there, I just wanted to emphasize that this is where the power of a multimodal database lies. The edge index helps in performing graph queries in an order of number of neighbors rather than doing index lookup in each while performing a join in a relational database style fashion when we are serving a query which has like a query of graph nature. I think that's where the power of a graph database lies, that it is basically able to get all my neighbors in order of number of neighbors without doing any more than necessary index lookups.
Yes, that's absolutely right. And there's one more aspect I would like to mention here. In case you have edges which are many edges which are adjacent with the same vertex, you have a separate problem. Because quite often you don't want to see all these edges coming out of this vertex, but maybe you want to filter on some kind of timestamp and just take the outgoing edges. Say you have a super node and 1 million edges coming out of the node, and you just want to see those 10 which fulfill a certain condition on the timestamp. Then you need a concept called vertex-centric indexes, which means that you essentially not only have the edge index, but you also have a kind of index on the set of edges coming out of a single vertex. Because then you can very, very quickly home in into exactly those few edges you need. And that is actually for a certain type of graph traversals also quite important. And that we essentially do by using sorted indexes which first sort by the from attribute and then by potentially other attributes.
I see. Great. So let's move on to the transactions in ArangoDB. So the documentation of ArangoDB states that it provides multi-document and multi-collection transaction on a single instance of ArangoDB. How does ArangoDB ensure that?
Yeah, for a single instance, we have a transactional storage engine, because the storage engine is now the storage engine for the complete database. And so therefore we can use either the transactional facilities of RocksDB, or we can use the transactional features of the file storage engine to directly provide full ACID semantics for multi-document, multiple collection operations. In a cluster, it's not quite that easy, because although the storage engine we have is transactional, it's transactional on a single database server. And so therefore, at this stage, I'm unhappy to say, but I have to say that we only offer ACID guarantees in a cluster for single document operations. So the atomicity here is on a single document, because a single document will always be on a single document shard leader, and so therefore we can enforce that. However, we have plans to implement distributed transactions, and one of my big dreams is that I see this headline on Hacker News, ArangoDB now with distributed transactions. Once I see that, I'm a happy man.
Great. Yeah, definitely. That will be something to have distributed transactions because they are not easy to implement. So just so that the listener gets a clear understanding of how the transaction work in ArangoDB, can you discuss the read, write, and exclusive collection types which are specified by the client which is making a query? How do they fit in this transaction model?
Yeah, currently you get two ways to execute transactions in ArangoDB. And recall, this is just in a single instance. One way is to use the AQL language, the Arango query language, which is by definition transactional. So if you do a read, you will always see a consistent snapshot with one read transaction. If you do a writing thing, then this will always be a single transaction, unless it becomes too big and we have to do intermediate commits because of limitations. So therefore, on a single instance, this happens behind the scenes in AQL. A second possibility is that you send a JavaScript function, and recall that we embed the Google's V8 JavaScript engine. You send a JavaScript function which essentially executes as a transaction. So all the manipulations that function does to your data are implicitly wrapped into a transaction, and if the whole thing fails or throws an exception, then everything is aborted and the transaction is aborted. And if it ends normally, then it's committed and the transaction is finished and has committed. So that's the model for transactions we have currently. But when we move to cluster-wide transactions, we will probably have a model where you use an API call to start a transaction, and then you perform multiple operations within the context of that transaction, and in the end you send either commit or abort. So that is something we will probably move to, but that is not currently there.
I see. So anytime an ArangoDB transaction is performed, it announces that which all collections it will be using in read mode, write mode, or exclusive mode. So when we are serving, let's say, a graph query where we don't know what all collections we will end up making the query on just because of the nature of the graph, is it possible that we enter into a deadlock? And if that does happen, how can ArangoDB recover from it?
Yeah, for this particular reason, we require that you name all the collections you want to use in a graph traversal before you actually use them. Because otherwise we could not prevent that kind of deadlock from happening. So in particular in a distributed system, that would be disastrous. And so therefore we can do deadlock protection against that, and this doesn't happen. But you have to name all the collections which appear in your graph. In the most situations, you will have one vertex collection and one edge collection for the graph, and it will not actually be a problem. But you can use multiple edge and multiple vertex collections, and then you simply have to name them.
I see. So one last question on transactions, which I had, so that the listener kind of gets an idea of how transaction works in a clustered environment. ArangoDB currently supports single document distributed transactions. Is that correct?
That is right, and you have a kind of compare and swap operation. So you can say this write operation is only to be executed provided the current version of the document is this one.
I see. So are we using like a two-phase commit kind of protocol to enforce that?
No, we don't have to, because the shard leader for every shard is responsible to serialize and to ensure the atomicity of the document operation for that particular shard.
I see. So, but if that transaction is happening is across multiple nodes, so then how do we ensure that all the nodes in the participating in that transaction are in sync? Do you kind of get what I'm getting on?
Yeah, that is why we only support transactions with single documents. We perform the transaction on the shard leader and synchronously replicate to all replicas before we tell the customer, yes, this transaction has happened. The shard leader serializes the operations for that particular shard, and the replicas just do the same transactions one after another. And this comes back to the other thing we covered. Provided some of the followers fail, they are temporarily dropped as in-sync followers, and we can move on, and later the system will repair itself by synchronizing within the cluster.
Great. So now that we have discussed many aspects of ArangoDB, one of the last things which I wanted to discuss was the horizontal scaling of ArangoDB. Since we support 3 different models in ArangoDB, how are the challenges different for different model when it comes to scaling?
That is a very good question. So for the key value model, it's trivial. You simply scale and there's no problem. Sharding is done in a hash-based fashion, and that poses no particular difficulty. For documents, it depends on the query. If you just do simple document lookups or use a simple secondary index, it works equally well. A secondary index on a sharded collection is nothing but an index on each shard, and so we can just use the usual indexing locally and then put the results together on the coordinator. But when it comes to more complex queries like join operations and so on, then yes, scalability is a challenge. So for this particular purpose, we do our best to make our query optimizer aware of this. And in the enterprise version, we have something called satellite collections. That is a feature where you can take a relatively small collection and simply say, you are a satellite collection, you are replicated in a synchronous fashion to every single node in the cluster. This means that a join operation between that satellite collection and a larger sharded collection can be pretty fast, because it can be done locally on each shard of the large collection, because a copy of the small collection is available everywhere decentrally. So that feature enables us to scale better in a lot of cases where complicated join operations would otherwise be a challenge. Now, the last storage model is for graphs. And here, scaling is particularly difficult. Imagine a graph which you just in some kind of random fashion distribute all over the place. You want to run a graph traversal, you have to hop between nodes in an incredible fashion, and it becomes awfully slow. And looking up an edge or something like that in local storage can be as fast as a few hundred nanoseconds. whereas a network hop can be 1,000 or 10,000 times slower. So that is really, really a big challenge. And we address that with a feature called Smart Graphs, which is again only the enterprise version, which does essentially the following. Most of the time, you have domain-specific knowledge to be able to shard your graph in a better way, such that most edges are actually local on your nodes. And the smart graph implementation makes use of that fact. The user has to give a so-called smart graph attribute, which is then used to do the sharding of the vertices and edges across your cluster. And if this has been done properly, most edges are local, and our algorithms for graph traversal make use of that fact by essentially doing as much as possible of the transversal on each local node, and only reporting the results when we have to do jumps between nodes. And that can speed up graph traversals by typically a factor of 10 or 100, and is what we do to scale graph traversals, which in principle are a challenge for scaling.
Right. So that's a pretty interesting couple of things which you mentioned about smart graphs and the satellite collections. Satellite collections to kind of scale the document store, and the smart graphs to scale the graph model side of the multimodal database. So the last question, because we are running out of time, is regarding the performance comparison. I on the website, looking at the graphs which were comparing ArangoDB with other multimodal database and also the single model databases, ArangoDB seemed to be doing at least as well as all those. How do those numbers look like in a clustered setting?
Yeah, in a clustered setting, we have done comparisons as well, but mostly using relatively simple queries. So in a clustered query, you are interested on whether single document operations or single document lookups or writes scale well, and we have demonstrated in one performance benchmark that we can really linearly scale with a number of instances. Yes, smart graphs and satellite collections are good, but you can never expect trivial scalability. You can never say with 10 times the machines I'm 10 times as fast. This is simply, there are theoretical limits to that. And so therefore, and the other thing is it's actually difficult. There's not that many distributed graph databases. There's not that many distributed data stores which can actually do complex operations and so on. So therefore, the ground to cover with benchmarks is there a bit thinner.
Great. So I think at this point of time, we are at the end of the show. Is there something which you would like to say to the audience, or is there something which you feel I did not ask but you wanted to cover?
There's actually two things I just would like to mention briefly, because people can then look up them. First of all, we have a JavaScript framework to actually deploy extensions to the database directly to the database server. I mentioned that we embed V8, the Google V8 engine. So our Fox framework allows that you can actually extend the API of the database with your own JavaScript code. That gives a lot of possibilities, like schema enforcing, like a very flexible design of your microservices and so on. I don't want to go into much detail. That framework is running on the coordinators and can be scaled independently from the database servers in this way. And it's also a great extension for capability. And the second thing I want to mention is that deployment has become particularly easy now because we have a Kubernetes operator. So that means essentially deploying an ArangoDB cluster with replication and everything, and metrics and so on, becomes essentially as easy to as you install an app on your phone, because you just take a little YAML file of 10 lines and deploy it to your Kubernetes cluster, and suddenly everything is fired up and works like magic. There will be no more about this in our publications, but these are the two things I really wanted to mention.
Great. Yeah, I wanted to discuss the Fox framework, but we are running out of time, so I did not get a chance to deep dive into it. But maybe I can invite you some other time and we can discuss other aspects of ArangoDB which we were not able to cover today. So, Max, how can people follow you?
Well, first of all, we have a blog on the ArangoDB page where I occasionally write stuff. We have an ArangoDB Twitter account, which is just @ArangoDB. And that has interesting stuff. There's a newsletter you can ask for. And essentially, my complete work is on GitHub. So therefore, most of the work is done in the open source version, and one can see what I do. I also have slides on SlideShare. I'm myself personally not very active on Twitter, I have to admit. Just finding not the time to do that.
Okay, I'll include all the necessary links so that people can follow you in the show outline. So Max, thank you for coming on the show. This is Nishant Suneja from Software Engineering Radio. Thank you all for listening.
And thanks for having me.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.